Let's do some exercises in which we'll apply the properties of vectors that we've learned in previous presentations. So here let's find a vector of coordinates 1 and t. So let's find such a t for which vector of coordinates 1 and t is parallel to vector of coordinates. So this sign here, two vertical bars, means that the two vectors are parallel. It's parallel to vector of coordinates. Let's make it 2, 3. So here it's an algebraical interpretation of it. So here we have vector of coordinates 2 and 3, u, and v of coordinates 1 and t. So we have a family of vectors, and one of these vectors, when t equals to 1.5, is parallel to vector u. But this is solved empirically, and we want to solve this problem algebraically. Now let's look at the two vectors and what are their properties when they satisfy the condition of being parallel to each other. One is the scalar multiplication of the other one. So vector u, we can for example say that vector u is some scalar times vector v, which we apply to solve this problem algebraically. So now some scalar a times vector 1 t equals to vector 2, vector of coordinates 2 and 3. Now if we multiply a vector by a scalar, the result is a vector whose coordinates we obtain by multiplying each coordinate by a scalar a. So it is the same as a times 1, it is a, and a times t, it is a t, equals to vector 2 and 3. So all these algebraical statements are equivalent. This statement above is equivalent to the statement below, is equivalent to the statement here below. That's how we write equivalent statements, one underneath the other one. And this here means that two vectors are equal when the components are equal, respective components are equal. So a equals to 2 and at equals to 3. So here we have a system of simultaneous equations. Very simple because we don't have to solve for a, it's already here. We know that the value of a equals 2, which we can plug into the second equation. So once again, this statement above is equivalent to the system of equivalent equations below. So here we get that 2 times t equals to 3. Yes, and by dividing both sides by 2 we get the value of t equals to 1.5. Divide both sides by 2. That's what we got empirically here. 1.5. 1.5. Now, as an exercise, find x for which a vector of coordinates 2 and x minus 3 is parallel to vector of coordinates 4 and 2. So pause the tape and do the exercise. Okay. Now let's look at the geometrical interpretation of the problem. So here we have the vector of coordinates 4 and 2, vector u, and here is one of the vectors whose coordinates are 2, and the second coordinate is x minus 3. In this case, x equals to 0. Now, if x is bigger, you'll have a family of vectors, and one of these vectors is parallel to vector u. We can see that the vector of coordinates 2 and 1 is parallel to vector u. We are actually not looking for the value of the second coordinate, but for the value of x. So x minus 3 in this case equals to 1. But this is solved once again geometrically, empirically, and we want to solve it algebraically. So, as previously, the two vectors are parallel if one is a scalar multiplication of the other one, and we apply this fact by writing an algebraic statement. What it means that the two vectors are parallel. So vector 2 and x minus 3 multiplied by some scalar, could be, we can name it whatever, could be a, equals to vector of coordinates 4 and 2. And now, multiplying by a vector by a scalar, we have to multiply each coordinate of the vector by the scalar. So it is 2a, and the second coordinate is a times x minus 3 equals to vector of coordinates 4 and 2. Now, here we have 2a equals to 4. So here we have, because the two vectors are equal, their components are equal, respective components are equal. So the second components are also equal. A times x minus 3 equals to 2. Here we have a system of equivalent equations. So here we find the value of a. A is 2 by dividing both sides of the first equation by 2. And now we plug the value of equals to. We plug the value of 2 into the second equation. So 2 times x minus 3, 2 times x minus 3 equals to 2. And we have to find the value of x, so we divide both sides by 2 and we'll get x minus, so here I divide it by 2, so I'll get x minus 3 equals to 1. And now the answer to our problem is x equals 4. So if x equals 4, the two vectors are parallel, And if x equals 4, then the second coordinate is equal 1, but this is not the question. And what we got here, x equals 1. But this is the answer. For x equals 4, the two vectors are parallel.